Welcome to DCT maps, compact differentiable lidar maps based on the cosine transform. My name is Alexander Schaefer. DCT maps are a novel kind of continuous lidar map. They overcome three disadvantages of the very popular occupancy grid maps. Let's have a look at these disadvantages. First, grid maps exhibit aliasing effects. Wherever the edges of obstacles are not aligned with the grid, we observe the characteristic staircase patterns in our sample map. Second, grid maps are not differentiable, although this is a desirable property of every map representation. If grid maps were differentiable, we could localize the robot shown in the map by simply maximizing the measurement likelihood. Third, grid maps are based on quite an inaccurate sensor model. Consider the laser ray shot through the empty cell. The ray is not reflected in the cell, so the robot reckons that the complete cell is free. We obtain the exact same occupancy probability for the occupied cell below, although the distances the rays travel within the respective cells differ considerably. DCT maps overcome these disadvantages due to their substantially different formulation. First, they are based on a more accurate sensor model, the recently developed decay rate model. For each cell, the decay rate model not only measures the numbers of laser hits and misses, but also takes into account the distances the rays travel within each cell. Second, the map parameters are not stored directly in the spatial domain, but in the frequency domain. To determine the spectral map parameters, we maximize the measurement likelihood over the map parameters. To transform the spectral representation to the spatial domain, we employ the continuous extension of the inverse discrete cosine transform CE-IDCT. The resulting continuous DCT maps avoid the aforementioned disadvantages of grid maps. As a consequence of the spectral map representation, DCT maps do not exhibit aliasing effects in the spatial domain, and they are continuously differentiable. Consequently, we can localize the robot in the map by maximizing the measurement likelihood. The decay rate sensor model takes into account the distance each ray travels within each cell, yielding more precise maps. In addition, in extensive experiments, we demonstrate that DCT maps outperform not only grid maps, but also other continuous map representations like Hilbert maps and Gaussian process occupancy maps in terms of accuracy.